Covers Griffiths E&M, section 9.2.3, Energy and Momentum in EM Waves. Okay, so according to the previous chapter, in a section we haven't necessarily covered, the energy per unit volume of an electromagnetic wave can be defined by the expression U is equal to 1/2 epsilon naught E squared, where E is the electric field, times 1 over mu naught times B squared. Okay, so waves, electromagnetic waves, have energy. Okay, so let's go ahead and talk about a particular flavor of electromagnetic wave, and those are plane waves that are monochromatic or single wavelength. Okay, so one color, the waves are far enough away from the source that they're all moving in a plane, and then we can go ahead and define the electric field then as being some amplitude times cosine of the wave number, which is related to the wavelength. I'm going to have this move in the z direction, or the wave propagate in the z direction, minus omega t. Right. And I'm going to get rid of that phase factor if you're looking carefully at the book. Okay. So this is an EM wave. It's moving in the z hat direction. The electric field is pointed in the x hat direction. Right. And the magnetic field is then 1 over c times E0, because those amplitudes are related to each other, times cosine of kz minus omega t. This is pointed in the y hat direction. Okay, so in this case, I know that my amplitude here, B0, is 1 over c times E0. I can go ahead and square all of those, because that's fine to square both sides of that expression. And that tells me that, well, 1 over c squared is related to mu naught epsilon naught. So it's mu naught epsilon naught E0 squared. And therefore I plug those bits into this expression, and I see that I have 1/2 epsilon naught E squared plus 1 over mu naught times mu naught epsilon naught E squared. This is the contribution of the energy from the electric field, and this is the contribution of the energy from the magnetic field. All right, I just plugged in those two terms up top. But those are exactly the same. So I can go ahead and write the energy density as epsilon naught E squared, or epsilon naught times my field, E0 squared cosine squared kz minus omega t. So the electric fields and the magnetic fields contribute equally to the energies of these waves. Okay. So let's just specify, just to be really clear, this U is an energy density. So I have this wave traveling in some space, right? And I take a box and I add up all of the energy within that box, and I divide it by the volume of that box, so energy per unit volume. All right, great. So as waves move, they can move this energy. It wouldn't be very useful energy if the wave wasn't propagating the energy forward. So how does it move forward? Well, we can describe the way the energy is transported by calculating the Poynting vector. The Poynting vector is the energy that goes through an area in a given time. Okay. This is defined as S 1 over mu naught E cross B. This is 1 over mu naught E. I'm going to use this expression here for E and B. I'm left with E0, 1 over C, E0 cosine squared kz minus omega t. And now I need a direction associated with that. So E cross B is x hat cross y hat. X hat cross y hat, the way we define our right-handed coordinate system is that is in the z hat direction, which is convenient because that's the direction that I said that those waves were moving. All right, so I'm left with this expression, which I can write as 1 over, oh, that's not correct, 1 over mu naught E0 squared, 1 over C. Well, I can go ahead and rewrite 1 over C as C over C squared. That seems like a silly thing to do, but I'm going to do it. Times cosine squared kz minus omega t. The reason I did this is because 1 over C squared, we know what that is. 1 over C squared is mu naught epsilon naught. So that means I get an epsilon naught. The mu naughts cancel. I'll pull that C in front. E0C cosine squared kz minus omega t in the z hat direction. Oh, that's convenient because this piece right here looks a whole lot like the energy density modulo of C. So the Poynting vector says that the energy that moves, the waves move energy in the z hat direction. It moves the energy density with some speed c times z hat. So it moves all of that energy density at the speed of the wave. Okay, I think that makes sense, in the direction of the wave. Great. So electromagnetic waves have energy associated with them. They carry that energy, and they also carry momentum. We're going to go ahead and use the notation that Griffiths has here and use the definition from a previous chapter that the momentum of an electromagnetic wave, which we're calling G, is related to my Poynting vector and 1 over c squared. Okay, that is equation 829. Okay, so again, if I'm using plane waves with monochromatic or single wavelengths pointing in the z hat direction, I know what my Poynting vector is, so I can just directly plug that in from the previous slide. That is 1 over c squared times cu z hat, which is u over c times z. All right, great. So you have momentum and energy. Now, I have these waves that are traveling, and if I'm going to measure the momentum or the energy that's being traveled, or even the energy that exists in some region, my measurement is going to be over many of these cycles, right? I'm never going to be able to measure, sub an oscillation because these things are moving so fast or oscillating so quickly. Okay. So instead of saying what is the energy or what is the momentum, I should instead ask what is the energy averaged over many of these periods. Okay. So if you average over many cycles, or at least a cycle, I take that energy, the average energy, okay? So I need to take the average of U, which is epsilon naught E0 squared cosine squared kz minus omega t. All right, this is a constant, this is a constant. The only thing that's changing in time is this cosine expression. So I can pull these out of the average, and I'm left with the average of cosine squared over kz minus omega t. Now, as long as you are looking over, at least over a period, or many periods, likely, this cosine function has a well-defined average. Okay, the average of cosine squared of anything is 1/2. So I'm left with 1/2 epsilon naught E0 squared. So therefore, I can write my pointing vector as something that's related to the average. So UC Z, so the average of my energy times C in the Z hat direction, which is borrowing the line from above, 1/2 epsilon naught E0 squared times C in the Z hat direction. That's the average. And then my average momentum is average U over C in the Z hat direction, which is 1/2 epsilon naught over C E0 squared Z hat. All right, so light has a well-defined energy density. The rate at which energy travels can be determined by the pointing vector, and it has a momentum associated with it as well.